I think there was just turn your phones off and we will begin. And my name is Vasily and I am presenter, so there is no useful information. Don't. I think we can start, and you will not be worried about present me and tell everyone to silence their phones and so on. So, okay. Hello, everybody. My name is Vasily. I am software developer in Yandex. I am the main developer of GPU version of this library. And today I will talk about what is CatBoost, what problems it could solve, and give you a tutorial. This library was developed in Yandex. For everyone who doesn't know, Yandex is a Russian IT company. It's the biggest search engine in Russia. It's bigger than Google in Russia. No, not in the world. And we've been using gradient boosting for many, many years to solve our production tasks. I think the first version of our internal library of gradient boosted decision tree library was developed in 2007 when there was no XGBoost, and we've already solved problems on very big data sets with our internal gradient boosted decision tree library. And in previous summer, we've released in open source our latest version of gradient boosted decision tree library, and this library is CatBoost. Before we will go to the tutorial, I want to briefly discuss what CatBoost is, what is gradient boosting, and what problems we could solve with gradient boosting, because it's a tutorial for everyone. And firstly, I want to ask a question. How many of you knows about gradient boosting? Please turn your hands up. Okay, good. And the second question, how many of you heard about CatBoost before this tutorial? Okay, that's also good. So there will be useful and new information for everyone, I think. Okay, so what is CatBoost? CatBoost is a machine learning library that is designed to solve supervised learning tasks. We have several different types of supervised learning problems that we need to solve, and they could be classified by type of inputs that we need to deal with. For example, inputs could be images. For images, we need to use convolution neural networks. They provide you very good results, and it's the state-of-the-art technique. CatBoost is not a neural network. It's a library that works with structured data. And for structured data, we have structured data is a very classical type of inputs. We have a matrix. There are rows in matrix, columns in matrix. Each column is a feature or a predictor, and each row is some observation. For each observation, we have label, and we need to predict this label based on a description of observation, based on a vector of features. And for such type of inputs, we have a very good technique. It's called gradient boosting, and it's gradient boosting on decision trees that provides you a state-of-the-art results. This technique builds an ensemble of decision trees. Ensemble is a linear combination. We have several decision trees. We apply them, and we have some prediction. This technique builds this ensemble in greedy manner, and this ensemble will give you very good results on structured data. Usually, these results will be the best that you can achieve on this data set. This technique is very, very powerful. It could be used not only on very big data sets, it could be used on small data. And because of this, boosting has very big number of applications. You could find applications of boosting in research, in industry, and today it's very well known because of competitions on Kaggle. Almost any competition where we have structured data will use some boosting library as part of winning solution. And here on the slide, you can see some examples where you can apply gradient boosting. And don't think that it's everywhere. There are these all examples that could be used. You could use it almost everywhere. Whenever you need machine learning and supervised learning, you almost always could try to use boosting in some way. For example, you should not think that neural networks and gradient boosting are competitors. These techniques are not competitors at all. They could be efficiently combined together. Gradient boosting works with structured data. Neural networks will work with unstructured data like images. And let me give one example. assume we need to predict if the person is ill. For this, we could go in a classical way. We could measure temperature of person, measure blood pressure, ask him some questions, and make some other predictors based on our problem domain knowledge, create a vector, gather historical data, and train model. We could start with simple linear model, then we could train gradient boosted decision tree model, and use this model to predict illness of person in the future. Or we could have some hardware like X-ray that produce us some raw data like image or some other signal, and we could train neural network and solve the same task. Or what is better, we could combine raw data and use neural networks to work with raw data and gradient boosting in one model, and this will give you benefits. It's very simple. We just train neural network on some images, for example. Then we have a vector with probabilities. The predictions of neural network is probability. This probability that the person is ill. We take this probability, add it to a matrix that will be used in gradient boosted decision trees, and that's all. We could train model on the set with just classical structured data and predictions of neural network. And this usually provides very good results. So to work with gradient boosting, we need just one thing. We need to ensure that columns in our matrix are numerical ones. Gradient boosting, when we work with decision tree, could work only with numerical features. It's classical type of features. We could compare two values and say if one is less or other is or otherwise. And in decision tree, we will then use feature value. We will select threshold and split the data based on some condition. So such features are natively supported in decision trees. But in real-world data, we have one more important type of inputs. It's categorical features. And for example, in pandas datasets, pandas data frames, we very often will use some columns that are not numerical ones, but categorical, like text or string and so on. And working with such predictors is pretty hard task. It's not very easy to use them in decision trees. There is one technique that almost everyone knows. It's one-hot encodings. This technique provides good results, but only for categorical features with small number of distinct values. For example, here on the slide we have categorical feature occupation, and there is just five different values. But in real-world data, we have categorical features like hashtags, for example. They have millions of different values, and working with such predictors in decision trees is hard. We can't train model. We can't train a good decision tree model, good ensemble of decision tree to work with such big number of distinct values. So there exist several techniques that allow us to work with categorical features with high cardinality. And in CatBoost, we've implemented them, so CatBoost could work not only with categorical features with small number of values, but for categorical features with high cardinality. And you don't need to do anything. You just need to set in your input matrix a column, provide in input column some text instead of float number, and everything will work. But I will talk about this later. So CatBoost is a library that could work with categorical features. It's our advantage, and our techniques allows CatBoost to achieve state-of-the-art results on publicly available datasets. Here you can see a table. We compared our library with our competitors. It's LightGBM, XGBoost, and H2O. We've used publicly available datasets and tuned hyperparameters of each library with hyperopt. And results are here on the slide. Sometimes CatBoost is significantly better, like on Amazon dataset. Sometimes it's just slightly better, but nevertheless, CatBoost will give you very good results. Here we've compared logarithmic loss. This is objective that each library optimizes. So if you have a set with categorical features, then it's definitely a good idea to try CatBoost. Okay. When we deal with boosting libraries, everyone wants not only quality, but that library works fast. And sometimes people think that CatBoost is not a very fast library because we have special techniques that works with categorical features. This technique is computationally pretty expensive. And all our competitors does not have these techniques. These techniques, and when someone trains model on set with categorical features, CatBoost could be slower than other libraries because other libraries don't do anything to deal with categorical features. And so they probably will not have very good quality, like you see on the previous table. But when someone needs to work with just numerical features or with numerical features and one hot encoded features, then performance will be very good. Firstly, our CPU version will be comparable in speed to the other libraries. To prove this, we've measured time that we need to learn 100 decision trees with a similar complexity on 3 datasets. The sets you can see on a slide, it's the sets just with numerical features. And as you can see, sometimes CatBoost is faster, like on epsilon sets, sometimes it's slower, like on Higgs or cover type. But CatBoost still works not significantly slower than competitors and could be used to train models. But this is CPU version. When we need to deal with very big datasets, it's a very bad idea to use CPU. And these datasets are not examples of big data. These datasets are small. And even for them, it's not a very good idea to use CPU. You will need several hours or even several days to do grid search or some hyperparameter optimization to train models on these datasets. Today we have GPUs. GPUs are fast, and gradient boosting on decision tree could be efficiently accelerated on GPU. For example, here on a slide you can see a chart. This is relative speedups of several different GPUs compared to CPU for our library. We have GPU version, and this GPU version significantly faster than our CPU version. Here we've used 56 logical cores CPU. It's very powerful CPU. It's dual socket, and you will not find such CPUs in desktops, for example, usually. And we've used several modern GPUs. Even old generation GPU is 4 times faster than CPU. On x-axis there is a number of samples in the sets, and we've fixed number of features. So we have the sets. We have the numerical dataset, dense numerical datasets with 800 features and different number of samples. The more samples you have, the faster GPU, the bigger difference between GPU and CPU will be. And if you have approximately 4 million samples, then GPU will show the best results. It will be almost 40 times faster than CPU, the most powerful NVIDIA GPU. One important thing here, I've used Tesla GPUs. It's a very expensive GPU, but we could buy NVIDIA Titan V. It will provide you similar to V100 speedup. It will be almost 40 times faster, but it will cost you the same amount of money that this Intel Xeon CPU. And the difference is very big. So we have very good GPU version, but it's not only faster than our CPU version. This GPU version is faster than our competitors. Here on the slide, the same datasets that I've showed you before, but now we compared our GPU version with GPU versions of our competitors. And picture says for itself, we're now faster. And we sometimes 20 to 40 times faster than competitors. And one important thing, these datasets again are small. Our GPU version could work not only on one GPU, we could work on several GPUs. And for this, you will see even better results. And I think LightGBM can't even work with 2 or more GPUs. And my experience with XGBoost says that it's not very well on GPU for big datasets, but it's only my. Okay, now, the last thing that should be noted. When we speak about performance, we usually speak about training time, but the training time matches when we solve some Kaggle competition or do some analysis. When we need to solve production task, we want to not only to learn fast, we need to predict fast. Because we will learn model, then we will ship it to production, and we will need to answer the queries for users. And very often, it's time-critical service. And we have special type of decision trees. And because of this, we could apply our model very fast. Here on the slide, we've compared prediction time for our library and our competitors, and we 20 to 40 times faster. So it's a very big difference. And what this gives us?
How big are these models? How many trees are there?
It's, I think, 4,000 trees. We've applied it to Epsilon dataset with 500,000 samples, I think. And I think there was depth 6 trees, something like this. But I don't remember the exact numbers because benchmark was made by my colleague. But it's just an example. We will be significantly faster because decision tree hard to apply, and we are using special type of decision trees that's very easy to apply, and other libraries can't be as fast can't be so fast because of the design decisions. Okay, and one more thing about this slide. The first 3 columns are time we need to apply in one thread, and the second 3 columns are time we need to apply in 32 threads. Okay, so this performance gives us very great benefits. In boosting, boosting has one nice property. We could gather more data, and if we have more data, we will train better model. Also, we could increase ensemble size, and this also gives us benefits. If you could learn just 2 times faster, then you could take 2 times more data, and in real-world production scenario, you will train in the same time a better model. Again, if you could apply the bigger model in a special time restriction, then you could. This also will give you very great benefits. With CatBoost, you could train very big models because we could learn them fast and we could apply them fast. And this provides you benefits and quality if you solving your production task and you could gather more and more data, and your restrictions are hardware and not data set that provided you by some competition, for example, on Kaggle. Okay, so a brief summary of I've talked about everything I talked about. Today we will talk about gradient boosted decision tree library. It's CatBoost. It works with numerical features like any boosting library, but we also could work with categorical features. We provide state-of-the-art quality for categorical features. Our library is very efficient. We have very good CPU version. We have the fastest GPU version today of openly available boosting libraries today, and we could apply models very fast. And finally, our library is easy to use and has good visualization package, and this I will show you in the second part of our talk in tutorial. So for the tutorial, you will need to download IPython notebook. There is a link, there is QR code. You could just scan it and get the link. And you will also need to install dependencies that are here on the slide. I think I will give you 2 or 3 minutes so you could download everything, install, and we will switch to the next part of our talk. And maybe it will be a good idea if you will just photo this, so you could, if we'll go faster, then you will have everything. Okay. And while everyone installs, I could ask some questions, so we will not spend time. Okay, are you ready? Could you continue? Okay. So now I will switch to Python and will show you how to use CatBoost. Okay. Okay, so one moment, I will make me a mirror display. Okay, so today we will learn how to use CatBoost. CatBoost has a Python package, and so today it's a PyData, but just for your information, we could also work from command line, and we have a package for R. But today we will use Python. And today we have a tutorial based on Amazon Employee Access Challenge. This is the data set with categorical features, and we need to solve classification problem. So today's tutorial will be only about classification, but if you will need to solve a regression task or learning to rank, then CatBoost also could do this. If you want, I could make it slightly bigger. I think it will be good. Okay, so in first cell, just dependencies. They were on a slide. If something does not work, you should check that every package is installed. And check, please, that your version of CatBoost is the most recent one. Some parts of tutorial could not work on old versions of CatBoost, like 0.9 or 0.8. Okay, so when we solve supervised learning task, the first thing that we need to do is to load dataset in the memory, and maybe preprocess it, split our dataset to matrix with features and vector with labels and so on. Today, you don't need to download anything by hand. We provide the set we will use could be downloaded automatically with the helper function from our package. So in CatBoost we have package datasets, and in this package we have the set Amazon. Just like in current cell, we could download data frame. We could download Amazon learning set and test set in pandas data frames. So I've just done it, and here I have two data frames. Each data frame is Amazon dataset has 9 categorical features and label vector. First column of the set is action that we need to predict. It's just 0 or 1, and the next 9 columns are our features that will be used in our machine learning model. In this table, categorical features are just numbers. Why? Because Amazon doesn't want to provide us the real data, and this was obtained by some hash function. When we will use CatBoost to solve your production tasks or solve some competitions, you could also provide just strings and you don't need to make it numbers. Okay, so firstly, let's split our dataset to vector that we need to predict and to matrix with features. Okay, when we will need to deal with CatBoost, you will need to always do the one important thing. You will need to decide what columns are categorical ones and what columns are numerical ones, and store somewhere this information, because CatBoost can't automatically decide for you if column in input matrix is categorical or if this column is numerical one. So today our set has only categorical features, so I've created a list with in which all features marked as categorical. We have 9 features, and so this is sequence of from 0 to 8. Just before we will start some learning, let's look at number of zeros and ones in our target vector, in our labels, so we know how many zero classes and ones, because for classification tasks it matters. When we solve problems on imbalanced datasets, it's harder than when we have balanced data. And today our dataset is imbalanced. We have just approximately 2,000 of zeros and almost 31,000 of ones. To work with CatBoost, you need to create a special wrapper class that will provide CatBoost access to a data in our optimized way. All data should be in CatBoost. We have a class pool. This class stores the data in a format that CatBoost could deal with, because we want to learn efficiently. We could create our wrapper class that will be used to store the data in several different ways. Firstly, we could create it just from pandas data frame. For this, we will need to provide an argument data with a matrix with features. Or it could be NumPy array, NumPy matrix, or it could be a pandas data frame. Secondly, we need to provide a vector with labels. And finally, we need to provide argument cat features. This is a list with the indices of categorical columns in our matrix. And just like this, we could create our internal dataset that will be used in learning. This dataset could be created explicitly, like I did this here, or when we need to train our model, it could be done implicitly. I will show about use this, but it's not very efficient. When we pass the data like this, we will need to copy everything from pandas data frame to our internal format. And if your data is very big, if you have dataset, for example, for 100 gigabytes, you will need to copy everything, and you could run out of memory. So CatBoost provides you a way to load the data in memory automatically from a disk. What's more, it will do it efficiently. If you need to load data in memory with pandas, for example, then that very big dataset will be downloaded very slow. I tried 100 gigabyte dataset, and it took me, I think, 2 or 3 hours to download it in the memory. And CatBoost will do this significantly faster in several minutes. Okay, so let me show how to download the set in memory with CatBoost. Firstly, we need to save it. So we have a file from which we can load everything. So in this cell, I will save our dataset in 2 formats. Firstly, it will be tab-separated format, and secondly, it will be comma-separated format. And now I have on a disk 2 datasets. In the next 2 cells, I looked at them, printed first 2 lines, and CatBoost could automatically load the data from both files. The only thing that you will need to do is to create a description of columns. I said before, and I will say it again, I think, that we need always specify indices of categorical columns. And for users, Python users, we provide you a special function, a function that could create a description of columns for CatBoost. When we load the data from a disk, we need to provide a file, column description file, which will describe you a type of each column in your dataset. Or if I want to be more precise, this file should describe only categorical columns and index of a label column. All other columns are assumed to be numerical ones by default. So To Python users, we provide in CatBoost utils a special function, create CD function, that could create these files automatically from a code. This function needs three arguments. Firstly, it needs the most simple usage of this function. Firstly, we need to provide index of label column. Secondly, we need to provide indices of categorical features. And finally, we always need to provide where we need to write this file. Also, optionally, you could provide names for each feature so that when we will print the model or look at some analysis of model, we will have names of features instead of indexes of them. And so in this cell, I created this file and write it to amazon/train.cd file. And content of this file is here. We have tab-separated file. First column is index of column. Second column is type of column. In our set, we have 0 column is label, and all other columns are features, categorical features. So we have file like this. In the next several cells, there are examples that some parameters are optional. For example, we could skip specifying feature names, and then this file will have no names for features. Secondly, sometimes we have the set with not only categorical features, but with numerical ones. If we will not specify these columns, then in this column description file will be entries like this, where we will write that column is numerical and not categorical one. Okay, so you could, if you work with IPython, you could look at documentation and see what this function could do. Okay, after we created this column description file, we could load the data to the memory from TSV or comma-separated file, and this could be done just like this. We need to set the data option parameter to path for a file. We need to set column description option to path for a column description file that we've created before. And then CatBoost will do every work for you and download and create instance of pool class. Later you will be able to use this class to load, to train models, to apply them, and so on. Okay, one more thing. The most efficient way to create a pool class is to download it from disk. But in some applications, you still want to do a work in Python. For example, you want to preprocess your data with, for example, NumPy, and then train a boosting model. Or you want to apply model. We provided a special wrapper class called features data. I don't know why, but my IPython does not show documentation, so I will not able to show you its parameters. But this class requires just two main arguments. Firstly, you will need to provide a NumPy array with categorical features. This is a NumPy matrix with categorical features. And secondly, you will need to provide a NumPy matrix with numerical features. And if you will use features data class, then CatBoost will try to copy or access the data as efficiently as it could be done. For example, we will not copy numerical features to our internal format. We will use them just pointers from NumPy arrays. But this can't be done for data frames, and so there will be an overhead some if you will use pandas. And to work with features data class, if we work with features data class, we could create instances of our pool class just like here in a cell. Firstly, we created features data wrapper for NumPy matrix, and then we provided it to as argument for a data of our pool class constructor. And this class will be created more efficiently than from pandas. Oh, I understand why there is no documentation. It was here. So, documentation for features data. We need to specify numerical matrix, we need to specify categorical matrix, and optionally we could provide names for features. And with this class, we will be able to efficiently start the training. But usually, you should use this class to make predictions and not to train models, because most important thing, this class was firstly designed to allow users to store their description of their features in NumPy arrays and to apply models fast. But for training, it's also useful. Okay, so we've created three different pools. They are called data. We could train on each pool instance CatBoost model, and the set stores the same information. Here I printed just that the sets are of the same size, but you could also check that data in these classes are the same. So this was first step that we need to do. We need to load the data in memory. After we will load the data in memory, we could start training models. For the rest of the tutorial, I will assume that we have one training set and we have a validation set. And here I just split our the set with all data to train and test set with 80% of a train. And so I have train matrix and I have validation matrix. Okay. When we deal with boosting and when we solve classification problems, we solve them by optimization of some objective function. In boosting, different objective function allows you to solve different problems. We have objective functions for regression, like mean square error or mean absolute error. We have special objective functions to solve ranking tasks, and we have objective function for classification. Usually, there are two main types of objective that are used in classification tasks. Firstly, it's algorithmic loss, and this objective is used when we have zeros and ones as a label. Secondly, it's a cross-entropy target. This is generalization of logarithmic loss to a situation when for each observation, we have not a label with 0 on 1, but we have a probability that this observation belongs to some class. And when you work with CatBoost, you need to specify your loss function dependent on problem you need to solve. For classification problems, we have several different, and CatBoost have several classes that could be used to train models. Firstly, we have, I think I missed it. We have class CatBoost, and this is most generic one. Usually, you don't need to use it. It will not provide you all functionality, for example, for classification problem. It's most generic one, and you should use subclasses. We have subclass CatBoost classifier. This subclass provides you special methods to predict probabilities for classes, to estimate what class we need to predict, and also this class will automatically specify for you a loss function that should be optimized for classification. By default, this class will use logarithmic loss to train your models. But you could optionally change this loss function to other. And if you will need to use cross entropy, if your labels are probabilities, that you could just change loss function for cross entropy, and everything will work automatically. Let's train our first model. In the current cell, I created the basic instance of CatBoost classifier class, set some hyperparameters. In boosting, we have two main hyperparameters. It's the number of iterations and its learning rate. Usually, we train a model for several iterations with some fixed learning rate and look at test error on a validation set and stop training when our algorithm starts to overfit. For first example, I've just set number of iterations for 5 and learning rate to 0.1. It's just for example. And after we create an instance of our class, set hyperparameters we want to use, we need to call fit function, provide train dataset, provide evaluation set, and maybe we have some other parameters that will simplify everything. Will allow you to look at progress, to make plots, and so on. I will later show them. So this cell just our first CatBoost model. If trained model, we could after we trained the model, we have isFeatured function. This function will tell you that this instance of this class was featured on some data set. And we have getParams function that will set what parameters were used when you trained the model. Here I needed to specify learning dataset and the test dataset as instance of pool class. It's not very easy sometimes. For some experiments, you want just to pass data frame with a matrix with features, matrix with labels, and you hope that everything will work automatically, because some other machine learning libraries could work with such interface, and you could write generic code. Because of this, CatBoost could create instances of pool class automatically and without explicit creation of them like this. We could pass to fit function just a matrix with features, vector with labels. Then we need to specify what categorical features are, and we could specify evaluation set as a pair of matrix with features and a vector with values. And CatBoost will also learn everything automatically. But again, this should be used only on a small data sets, because for small data sets, overhead will be small. But when you need to do this with very big data, it is not a very good solution. And also, it's not a very flexible one. For different applications, for other objective functions, like ranking, you will need you will need to create instances of pool class, because you will need to specify some information like weights of classes, like how you should group the data to make ranking, and so on. And it can be easily done in syntax like this. Okay, so we fitted first model. Now we fitted a model without any information. When you train your model, you want to look at progress, how learning is going on, how many times we will need to learn models, what is error on validation set, what is error on learning set, and so on. Should we stop our learning? And in CatBoost, we could report you information about progress in several different ways. Firstly, we could write everything in standard output. Here is an example. We have option logging level. We could set it to variables. And after this, CatBoost will print you information about training automatically. CatBoost will create, on each iteration, CatBoost will write you several different columns. Firstly, it will write you error on a learning set. This is a value of objective function that CatBoost optimizes. Secondly, CatBoost will write you error on a validation set. This is a value of objective function on test set. And the next column is a best value. It's when we train gradient boosting again, it's an iterative algorithm, and for different number of iterations, we have different objectives. this column is an ensemble of is a number of trees that will provide you the best quality for your validation data set. So it's number of iterations that you should shrink your model after training so that you will have the best results. And then we have column with time that we spent learning our model. And finally, we have estimated time that CatBoost will need to finish the training. When we deal with gradient boosting and when we deal with decision trees, iteration time is almost constant, so we could estimate learning time very efficiently. And especially this is true for CatBoost, because in CatBoost we have special type of trees, and they usually train in constant time. Some other libraries like IGBM will need could train it in non-constant time, significantly non-constant. Okay, after the training will be done, CatBoost will print a value of objective function on a best iteration, just like this, and this iteration. And by default, CatBoost will shrink your model for this best iteration, so that your quality is as best as it could be. Okay. For more advanced users, we have other logging levels. If someone wants to look at decision tree that found on each iteration, they could create logging level info and look at more information. But I will not stop on this in details. Okay, so the first way to track your progress is to look at logs, to look at text information. Text information is not very useful. We could create images of plots for our learning error, for our test error, and this is more useful. It's much easier to look on a plot than to look at some text. And in CatBoost we have we could create visualization just in Jupyter notebooks, and this could be done very easily. We just need to specify plot option to true, and then CatBoost will create plots like this. Let me zoom this. So we started training. Now CatBoost will dynamically update plot during training. We will plot your error on a learning set. We will plot your error. It's a dotted curve, this one that goes down. We will plot your error on a test set. It's a solid curve. And also we will print time that we will need to spend to the remaining time. It will be, I think, here, and the time that we've already learned our model, it will be here, and there is a dot. It's a best iteration on a validation set. Okay, one more thing. This is our internal plot. It uses our code to make this visualization. CatBoost could also create plots in TensorBoard format. You could create and you could look at plots in TensorBoard, but I don't have this in tutorial. You could look at our documentation and see how it could be done. Okay. Now, today we talk about classification. When we talk about classification, we don't want to look at objective function that we are optimizing. We want to look at some more meaningful metric, like accuracy, like AUC metric, like recall or precision, or we want to look at F measure. These metrics are more you could interpret this metric, and this metric is more useful for users. And when we train boosting models, we also want to be able to shrink our model based on metric like accuracy, not on an objective function. We want to make plots of this metric, and CatBoost provides you several ways to achieve this. Firstly, we have option eval metric. This option is the main metric that CatBoost should care about. Firstly, this metric will be used to make plots in our widget. Let me run the cell. We will plot you this metric and show you everything about this metric on the first tab. Objective function will be also printed, but in another tab. Secondly, this metric is a main metric, and we will use this metric to shrink our model. Now we will not use objective function, we will use this evaluation metric. For list of all metrics that we could compute during training, look at documentation, but we could use, but almost any metric that you will need, I think is already implemented. If it's not, you could create an issue and we will do this. Okay, now, the second thing that we have, one more thing. I've told before that CatBoost will shrink your model. We have also, if you don't want to shrink your model because you have different metrics and you want to compute several metrics and then decide what amount of trees you want to use based on different metrics, then we have option use best model. You should set it to false, and CatBoost will not shrink the model. And here you can see that the best iteration was 23, but we doesn't shrink the model, and our model is all 50 iterations. Okay, now this was about one important metric. But sometimes we have one important metric like objective function on like accuracy, and we have several other metrics that we want to look at. For example, we could want to look at AUC, at accuracy, and at F-measure. And CatBoost could track these metrics automatically during training, and could use several metrics, not just one. For this, we have option, custom loss option. Here there is an example. We specify, we pass to CatBoost list of metrics that CatBoost should compute, run again fit function, and now we will plot you evaluation metric. This is logarithmic loss because I doesn't change it, and we will create tabs for these custom metrics, and we will plot you AUC metric and accuracy. So you could look at plots and again decide where you need to shrink the model. Okay, now let's look at a plot for AUC metric. You can see that here we don't have a dotted curve. This is a curve for our learning data set. Why? Because AUC metric and some other metrics are very expensive to compute. When you have very big learned data set and you compute AUC metric, and especially if this data set will have just several columns, then you will spend almost all time computing metric instead of doing learning. But in reality, you care about only error on validation set. So you don't need to compute a metric on learned set, and you don't want to spend time computing it. And because of this, by default, we don't compute some metrics on learning set. If you will need this, you will need to explicitly say to CatBoost that you should compute metrics. And for this, we have hints. We have several different hints in CatBoost. And the one that you will need to use is a hint that we should not skip train. By default, we skip train equal to true for AUC metric. We could change it just like this. And CatBoost will create you a dotted curve. This is error on a training set. Okay. Oops. And one more useful thing, if you want to compute AUC metric, but you still care about performance, we have option metric period, and we can compute metrics for you, not on each iteration, but with some interval. So here is an example. I've just computed metric, not on each iteration, but with some period. Okay. Let's look on the next useful thing that CatBoost has. How we compare boosting models? We could make a plot, look at plots, and decide what model is better. based on learning curve on a test set. CatBoost provides you an easy way to achieve this task. We could compare different models trained with different parameters. We could create plots just like this, but automatically from logs that CatBoost generates during queuing. When you start training of CatBoost, we create a so-called training directory. By default, it's CatBoost, and we store every information about learning in this directory. For example, there will be a file that will allow you to create TensorBoard logs. There will be a file that contains information about learning error, about test error, and also there will be a file that contains every information about visualization. If we will create for different training tasks different directories, then we will be able to later compare different models. Here I will train two models, provide training directory for different arguments. So there will be training directory named like this, training directory named like this. I will train two models. And after I will train these models, we have metric visualizer class. This metric visualizer class needs a list of directories where CatBoost stores logs, and it will automatically get the data that it needs to create plots and visualize everything. So now we have two different CatBoost models with different learning curves, and we could look at them and decide what model is better and how we could and need to adjust parameters. Okay. Now let's go to the next function that we have. When we deal with boosting, we usually train model until we start overfitting. On a new data set, we don't know how many iterations we should set. Because of this, usually it's everyone sets number of iterations. Everyone, maybe not everyone, but many people will set number of iterations for some big amount, train a model for this number of iterations, then look at curve and shrink the model, or like CatBoost, it will be shrinked automatically, but we will spend computation power for several iterations after we overfit. And this number of iterations could be pretty big. To deal with this problem, CatBoost provides you an overfitting detector. We have several different types of overfitting detectors. Some of them are designed to work well with functions with local minimums, like ones in ranking. But for tasks like classification, it's you usually could use a very simple overfitting detector. It's a overfitting detector that will stop training after the best iteration will be the gap with best iteration and current iteration will be bigger than some number of iterations. And this overfitting detector could be used just like here in a cell. We set early stopping rounds equal to some number and train our model. Then CatBoost will train model. Here the best iteration is 19. It will train for 20 more iterations, check that learning error is not, yes?
Are all the parameters the same as the XGBoost packages?
Almost every parameter, because we try to make it simple to users to change from XGBoost to CatBoost. So almost any parameter will have a synonym in CatBoost.
Okay, so it's like everything that I have in XGBoost.
Yes, we have a special function that will remap parameters. We have our own names for all parameters. New parameters we try to name just like XGBoost, so it could be very easy to switch. Thank you for a good question. I forgot about tutorial about this. Okay, so we could train model and see that we stopped our model. In our documentation, you could find information about other type of overfitting detector. It's slightly harder to use, but it in some applications provide you a better quality. Okay, now evaluation metric. This metric is the main metric, so if you will set this metric and you will use our fatigue detector, then CatBoost will use evaluation metric to shrink your model. So it's just so you won't be surprised. If you want to use evaluation metric, then it will be used almost everywhere. Now, the next thing, after you train just one model, maybe you want to make some cross-validation to estimate quality of your algorithm. For this, we have we've implemented a cross-validation function that will do cross-validation automatically. We just need to create parameters that we want to use for training. Now we need to specify explicitly objective function that will be optimized. In classification, I again say that it's logarithmic laws. And we have function CV in package CatBoost that accepts params. It's a dictionary with parameters that we want to use in training. It takes instance of pool class that we've created several times today, and parameters for cross-validation. Firstly, it's a number of faults. In this example, it's 5. Then it parameter inverted. This tells how we should do cross-validation. When we're doing cross-validation, we split the data for 5 faults, and we could use 4 faults for training set and 1 for test set. Or we could do otherwise. We could use 1 fault for training set and 4 for test set. And this says just this. Then we have 2 parameters that tells CatBoost how to make cross-validation. Should we shuffle the data before we will split for the faults, and a random seed to make it reproducible. And a plot function that will plot everything just as before. Here I've run CV. Now we created a slightly different plot. We will compute standard deviation based on several models that we learned. CatBoost will learn models iteratively, all 5 models for each fault. So we could use it in autostop and in other functionality. And we have this box. We could turn it off and look at errors for each model on a validation set. And CatBoost will return you a data frame. In this data frame will be errors, learn and test errors for all metrics, their mean and their standard deviation. Okay, and it could be used to access, for example, the best iteration based on cross-validation estimation. Now, one more useful thing in our cross-validation function. We could do not only classical cross-validation, we could do stratified cross-validation. When we have invalid datasets, we sometimes want to ensure that proportion of zeros and ones will be equal to proportion in all datasets in each fold. And to ensure this, we could split data with 0 classes and data with 1 classes to folds independently, and then ensure that proportion is one that we need. And for this, we have stratified equal to true option. Okay. I think I'm a bit slow today, so let's go to the next thing that should be discussed. When we train classification model, we obtain a model that reports you probability. Based on this probability, you need to decide what threshold you should use to select, to decide is this 0 class or it's 1 class. And this threshold almost always depends on problem domain knowledge. We could use a standard approach to say that everything that is greater, the probability for which is greater than 0.5 should be class 1 and all other should be class 0, but for many problems it's not desirable. Here I just trained a model. So in CatBoost we could help you with this task. we could create arrow C curve automatically. We could plot false positive rate, VC threshold curve, false negative rate, VC threshold curve, and select a threshold based on false positive rate or true positive rate automatically. Here is an example. Firstly, let's create arrow C curve. For this, we have a function in our utils. It's get arrow C curve. We need to specify a model. We need to specify data, and everything will be done automatically for you. Here in a cell example, we've created instance of pool class, created curve, and plotted with matplotlib. So we have curve, we could look at it and make some decisions. Now, if you want to look at false positive rate curve or false negative rate curve, we also could create them. You could look at documentation and see that we could create it based on model and data, as in previous example, or we could provide results from get arrow C curve function. And here an example of how to create a plot. And if you just want to set false positive rate, for example, for some specific value, we have a select threshold function that will create a decision based on false positive rate and false negative rate. Okay. Now, the next thing, assume you would train a model on a very big data set. You have for example, and you have machine that you have access, for example, for just 30 minutes. Or you want to train one model, then stop training and continue your training in some other day, and so on. For this, we have functionality to create snapshots. We could write our learning progress in a file, and then we could download our learning progress from this file and continue learning. To this, we need to set save snapshot option to true, select a file where snapshot will be stored, and interval with which we will write everything. And CatBoost will continue learning. I forgot to delete my snapshot, so I've already trained all 20 iterations, and CatBoost doesn't do anything. But I could set a number of iterations for a bigger number, and CatBoost will continue training. I had model with 20 iterations on my disk. CatBoost downloaded it and continued learning from 20 iteration to or 200 iteration to until 300 iterations. Okay, now after we'll train model, we will need to make predictions. To make a prediction, with CatBoost is very easy. We have for classification we have two main functions. Firstly, it's predict probe function. It just access instance of pool class, maybe without labels, and returns you a matrix with two columns. First column is probability of class 0, and second column is probability of class 1. If you will solve multi-classification problem, there will be several different columns with probability for each class. Secondly, we have function predict. This function will return you number at a label of a class that should be chosen. Okay, and finally, our predict function have option prediction type. If you know the math behind the sen, then you know that boosting decision tree will output not probabilities, but some value. You will apply sigmoid function for this value and obtain probability. And so CatBoost could predict this raw formula value results. This could be used, for example, to make some bagging on several models and so on, because it's sometimes not desirable to work with probabilities. And here in a cell, I just compare that after I will apply sigmoid, I will obtain this column. Everyone could check that they are just the same numbers and not, because here are just first three and last three, but they are equal. Okay, and now important thing about features data. I stated before that we have features data class that allows to make prediction and to allow us to make predictions fast. And it's especially true for numerical features. This example is for categorical ones, but the idea will be the same when we will use these numerical features. You could pass the data for predict proper function with a features data class, with instance of features data class, and CatBoost will compute the same predictions, but it will be significantly faster than if you will provide just NumPy matrix or pandas data frame. Okay, now we have one more useful thing with prediction. We could create predictions on some iteration. We have ensemble. There are several different trees, and we could compute predictions for ensemble of size 1, for ensemble of size 2, and so on. Even more, we could compute predictions starting from ensemble of size 2, then going with some step, compute predictions for ensemble of size 4, 6, and so on, and return you an iterator through these predictions. So you could implement your some custom metric function, create your plot for your metric, and create a learning curve for this metric, if this metric is not implemented by CatBoost already. And here is an example how we could achieve this. We call stage predict proper function, pass the data, pass the first tree we want to use, last tree we want to use, and period with which CatBoost will compute everything. And CatBoost will return you an iterator that will make predictions for ensemble of size 2, 4, and 6. Okay. One small example that CatBoost could also be used not to predict binary classification problem, but for multi-classification problems. This is very simple. You just need to change your loss function from logarithmic loss to multiclass. And a multiclass is a generalization of logarithmic loss for multi-classification. But when you deal with multi-classification, there are other ways to perform it. For example, you could train one versus all classifier, and CatBoost also could do this by changing loss function to multiclass one versus all. Okay. Now, after we train the model, we want to compute metric. Firstly, you could use stage predict proper function to compute your custom metric. But we have a big number of metrics that we've already implemented. And CatBoost could compute them for you automatically. In this cell, I just train one more model that I will use to create metrics. To create metrics, to compute metrics for our ensemble, we have eval metrics function. This function again accesses instance of pool class. It requires to provide metrics that should be computed, and parameters that you've already seen in stage predict function. It's the first iteration that should be used, last iteration that should be used, and step with which metrics should be computed. For example, if you want to compute them faster, then and you don't need a precise result on each iteration. And if you will set plot function to true, then CatBoost will create plots just like ones you've seen during training. So here is the result. And as a result, CatBoost will return you a dictionary. This dictionary will map metric name to an array with scores on each iteration. And here you can see result. Okay, finally, when you train your model, you want to save it on a disk, to share with someone, or to use it in a production service, and so on. To save the model, we just need to call save model function and specify file. In CatBoost, we have special format. This format is optimized for application, and we also ensure that we will be able to apply your models with CatBoost in future versions. So we have backward compatibility. You could train model today, and then we will be able to apply this model, I think, until our library will be used by nobody. And I hope it will be not very soon. Okay, so, and now, to load this model, we just need to create instance of CatBoost class called load model function and provide path for this model. And CatBoost will load it, and you will be able to apply it. Also, we could write our model in other formats. These formats optimize for other tasks. For example, we have JSON format that will present our model in human that human could look at and, for example, analyze this file, look at decision trees, and make some and get some information from this. Also, we could export formats to core ML format, and our models could be applied efficiently on Apple devices. And we have some other formats. You could look at documentation, but this basically will be applier in just C++, that is not very efficient, but it's just a code, or as I remember, it's a Python applier that's written just in Python code. Okay. Now, after you will train your model, you want to look at features, to look what features are important, how they are important, and how each feature influence predictions of your model. And for this, we have support for feature importance methods. Let's again train a model. Firstly, we have feature importances for that computed during training that will give you a basic idea of how important feature for this model is. This feature importances could be get just like this. We could call get feature importance with option prefeature equal to true. And this will be we'll get values for each feature from our information from training. And this feature importances will give you just one number. We could sort each feature sort features by this number and decide and look at this list and decide what features are important and what are not, and how they are important. But today, the most useful thing for decision trees to compute their feature importances is sharp values. This is a technique that was proposed on NIPS in previous NIPS. Everyone who sees shape values the first time, I suggest to look at their GitHub page, look at their paper. They explain how they're doing predictions, why they doing these predictions in optimal way. So they have a good motivation to make these predictions, to use for their algorithm, very good theory. And in CatBoost, we've implemented integration with a package that authors of shape values provides. So how to compute shape values for CatBoost? We just import their package, shape package, create explainer. It's created just like this. We need to provide a model. And finally, we compute shape values for instance of our pool class. And as a result, you will have shape values that could be used in a visualization functionality provided by shape package. You could look at plots like this. These plots will describe you how important each feature is for a single observation. Shape values is a feature importance based on observation. They report you influence they report you an influence of each feature for just single observation. And here, the bigger blocks is, the more important prediction, the more influence this feature has on these observations. And color is how it affects prediction. It will add some positive number for a prediction or some negative one. And such predictions could be computed for different observations, and they could be summarized. They could be summarized in plots like this, but for categorical feature, it's not a very useful plot. And what this plot contains. This plot will will show you a histogram for sharp values for each feature, and use a color. When we deal with numerical features, we could compare values of this feature, and for lower values we will use a blue color, and for big ones we will use red color. So we could use from this plots we'll be able to estimate if we have some monotonic relation with this feature. If, for example, we'll make a feature lower, then prediction will be higher. But today we have example with only categorical predictors, so this color is not very useful. And again, for more detailed description, I ask you to look at their documentation, because I just don't have time. We could create, if we want to just compute how important each feature is, summarized based on each data set, we could create a summary plot just like this, and here we'll have bars with importances for each feature. Okay, I think I skip these two sections, and I could answer some questions. Yes.
All the shape values is different from the feature importance which you earlier explained.
One moment. Different to these ones, yes?
Yeah. What is the difference? What is the usefulness?
For these ones?
For the shape values versus feature importance.
Okay, so shape values is feature importance based just on one sample. And this feature importance has a good motivation to access importance of feature for one sample. They could be generalized, these values could be aggregated through all that sets, computed mean value, for example, and be used as importance of feature for entire data set. But we have more older techniques that could be computed for each data set, and they could be computed during training. So these ones are features that computed during training, and this is a very simple technique that you could find in classical statistic books, and it should provide similar results that you will see by summarizing shape values. We first implemented this, and then there was a package with shape, and we add support for sharp values. Just like this. Okay. Yes.
So it seems like from your presentation, CatBoost is better than XGBoost in every way possible. So in what situation would you choose to use XGBoost over CatBoost?
I will choose to use XGBoost because I'm author of GPU version of CatBoost. If I will need decision trees from XGBoost, I will just write them. I know how to make very efficient decision trees, and because of this, if I will need some functionality from XGBoost, it's much easier for me to implement this. I could compare CatBoost with XGBoost, and then decide that I need this feature from XGBoost, and I should implement it, because basically I work with very big datasets, and I can't use XGBoost on this. But sometimes on some competitions, XGBoost could provide some benefits in quality, especially for people who know XGBoost well and know how to tune their hyperparameters. And in CatBoost, we have special type of decision trees. They have some limitations, and sometimes they could be slightly worse. Okay.
So you mentioned before that the parameters between XGBoost and CatBoost is basically the same.
Yes.
So if I use the same data set, I use the same parameters from both. Usually CatBoost will.
Oh, you can't use the same parameters. This is a problem. We have different type of decision trees. Because of this, we very often need a big ensemble. Like you could train 200 XGBoost iterations, and you need 500 for CatBoost. And also, you can't use the same learning rate, for example, because it just doesn't comparable.
Okay, so even though the parameters are similar?
They mean similar things, like how big your ensemble should be, how deep your trees should be, but they are not comparable in terms of quality. We will obtain other different models. You should always create learning curves and decide based on them. So, no more questions? Okay, then I think we could finish.